Today we'll continue learning about sufficient statistics and how we can use them to build estimators of parameters which are unbiased and have the smallest possible variance. This is called the minimum variance unbiased estimator. So sufficient statistics we will find are kind of essential if we want to have good estimators. So good estimators, I guess, so far a good estimator for us is kind of one which has small mean squared error. So that's kind of good. Another kind of good thing would be if an estimator is unbiased. But we know unbiasedness is not everything. But unbiasedness is kind of nice, as well as small mean squared error. So this result, actually this is a definition on this page, but it's leading to a result which says kind of the best estimator, in a certain sense, comes from a sufficient statistic, or it's always going to be based on a sufficient statistic. So let's talk about this minimum variance unbiased estimator. That's what this MVUE stands for. This is the estimator among all unbiased estimators for parameter theta, which has the smallest possible variance. Okay, so the definition might look a little confusing. We have theta hat, which is an unbiased estimator of theta. And then suppose theta tilde is some other unbiased estimator of theta. If the variance of our estimator theta hat is smaller than the variance of every other unbiased estimator, then we call theta hat a minimum variance unbiased estimator for theta, or MVUE. So it basically means the MVUE is the unbiased estimator which has the smallest possible variance among all unbiased estimators of that parameter, so of theta. Okay, so if we're looking at unbiased estimators, like if I have theta hat is unbiased and theta tilde is unbiased, so if they're both unbiased, then I'm going to take the one with smaller variance. Okay, so the name we give to such an estimator that's unbiased and has the smallest possible variance is the minimum variance unbiased estimator. So that's just a definition. We're going to be trying to find such estimators, trying to find the minimum variance unbiased estimators. And the theorem on the next slide is going to tell us where we should begin looking for the minimum variance unbiased estimator. And it tells us, in kind of a confusing way, it tells us that we should begin with a sufficient statistic. Okay, so this theorem, which tells us we should look for a sufficient statistic, so basically it says the minimum variance unbiased estimator is always a function of a sufficient statistic. Okay, I think maybe I have that exact thing written down here. And so the Rao-Blackwell theorem says this in a very complicated way. It first introduces some unbiased estimator called theta tilde, and it introduces a sufficient statistic for theta. So we have these two things, some unbiased estimator and a sufficient statistic for theta. Then it says, define a new estimator which is based on taking the expected value of theta tilde conditional on the value of the sufficient statistic. As a result of defining theta hat in this way, we get an unbiased estimator theta hat, and the variance of theta hat will either stay the same or get smaller. So we'll get something with variance, at most the variance of theta tilde. So basically, we can improve any unbiased estimator by conditioning on a sufficient statistic. Okay, what do I want us to really take from this theorem? Really just this. If we're trying to find the minimum variance unbiased estimator, what we should first find is a sufficient statistic for the parameter of interest. And then we just need to find a function of that sufficient statistic, which is unbiased for the parameter of interest. All right, so let's prove this kind of strange looking theorem. Okay, got it all cluttered. Let's say we've got, okay, so this is going to be proof of Rao-Blackwell. So let's say we've got theta tilde, unbiased for theta, and T is a sufficient statistic for theta. Okay. What we need to show then is that theta hat, which is some new estimator defined as the conditional expectation of theta tilde given the value of t, I want to show that this is unbiased, and I want to show that its variance is less than or equal to the variance of this guy that I started with. Okay, so let's first of all show that this new estimator is unbiased. Okay, so if I take expected value of my theta hat, so my theta hat, which is defined as the conditional expectation of theta tilde given t, I have expected value of this. Okay, so I'm just dropping this down in here. And now, if we think back to Stat 511, we had something where if I had two random variables x and y, the expected value of x could be written as the expected value of the conditional expectation of x given y. And in the same way, expected value of y could be written as the expected value of the conditional expectation of y given x. Okay, this was called like iterated expectation. And so this is really just expected value of theta tilde. Okay, because I can write expected value of theta tilde as the expected value of the conditional expectation of theta tilde given some other random variable t. Okay, and we began with an unbiased estimator. Theta tilde is unbiased, so I know its expectation is theta. So we have shown that defining an estimator in this way results in an unbiased estimator. And now let's work on showing this second property. Okay, so let's write down the variance of this new estimator, variance of theta hat, or rather, let's start by writing down the variance of theta tilde. Okay, we're going to use also an idea like this iterated expectation. We also had something called an iterated variance formula. So if I have x and y, then I could write, let me make more space, I could write the variance of x as the variance of the expected value of x given y plus the expected value of the variance of x given y. And the same way I could write variance of y as variance of expected value of y given x plus the expected value of the variance of y given x. So this was like iterated variance. Okay, so when I'm just going to use this to write down the variance of theta tilde as the variance of the expected value of theta tilde given t plus the expected value of the variance of theta given t. And now I'm going to note that this thing here is exactly my estimator theta hat. So what I really have is variance of theta tilde, just bringing this down, is equal to the variance of theta hat plus the expected value of the variance of theta tilde given t. Now to finish the proof, we just need to make this inequality appear. And we can do that by noting that this thing, being the expected value of a variance, has to be greater than or equal to 0, because a variance is always 0 or greater. And so the expected value of something which is 0 or greater has to be 0 or greater. So it must be that variance of theta tilde is greater than or equal to the variance of theta hat. Okay, so we've proven the Rao-Blackwell theorem. And I think the theorem is very confusing. So we can sort of convince ourselves that these statements are true, but the interpretation is kind of confusing. Like, these statements seem very kind of odd, but what's important is to just remember that we find the minimum variance unbiased estimator by using a sufficient statistic. Okay, so let me summarize in the next slide. There's an additional result which says if I have found something which is a minimum variance unbiased estimator for theta, then it is unique, so it's the only one. Okay, so there's only one minimum variance unbiased estimator. So we're just trying to find it. Okay, and the Rao-Blackwell theorem coupled with this one gives us kind of a two-step recipe for finding the MVUE. Step 1 is we just need to identify a sufficient statistic for theta. Having found it, since the Rao-Blackwell theorem tells us that the minimum variance unbiased estimator is going to be a function of a sufficient statistic, having found a sufficient statistic, we just find a function of that statistic which is unbiased for theta. If we can find that, then it's the minimum variance unbiased estimator, and we're done. Okay, we'll see an example of this. Let's say we want to find the estimator of some function of a parameter. We also just need to find a sufficient statistic for that parameter, and then we find a function of that sufficient statistic which is unbiased for, this should say tau theta. Tau theta. We'll see an example of this. Okay, so let's jump into an example. Here we have a random sample, x1 through xn, coming from an exponential lambda distribution. And I want to find this minimum variance unbiased estimator for lambda. That is, I want to find the estimator for lambda, which is unbiased, so unbiased, and which has the smallest possible variance. All right. In order to find this estimator, which is unbiased and has the smallest possible variance, we're going to use this two-step procedure. So first, I need to find a sufficient statistic for my parameter. Okay, how do I find a sufficient statistic? So we want to find sufficient statistic for lambda. All right, we got some practice in the last lecture finding sufficient statistics. It begins with writing down the joint density of all the random variables in the sample. We can emphasize dependence on lambda by writing this. Since these are independent and all have the same distribution, I can write the joint PDF as the product of these marginal PDFs. Okay, and if I want, I can include these indicator functions for the support. All right. So to find a sufficient statistic for lambda, I'm going to use the factorization theorem. So I'm looking to factor this into some function of the data and the parameter times some function of just the data. And then if I can identify this kind of function, that becomes the sufficient statistic. So let's simplify this thing. We've had some practice doing it already, so we get, I think we even looked at the exponential distribution, so I'm going to do this kind of quickly. Taking the product, it looks like this. Let's call this my function h, and let's call this my function g, and let's call this guy my sufficient statistic. Okay, the sum of the xi's. All right, so we've got sum of xi's as a sufficient statistic for lambda. So if I want to estimate lambda with an unbiased estimator which has the smallest possible variance, this is my starting point. I need to begin with this sufficient statistic according to the Rao-Blackwell theorem. So maybe what I should do is try to come up with a function of this thing which has expectation lambda. Let me try lambda hat equals 1 over n times the sum of the xi's. Okay, so this is a function of my sufficient statistic. And let's see if it's unbiased. So if I want to compute the expected value of this lambda hat, the expected value passes through the sum, and I get 1 over n times the sum of n lambdas. So I get n times lambda over n, I get lambda. Okay, so step 1 was find the sufficient statistic. Step 2 was get a function of the sufficient statistic, which is unbiased for the parameter lambda. So since I have expected value of lambda hat equals lambda, and lambda hat is a function of a sufficient statistic, I can say lambda hat is the minimum variance unbiased estimator for lambda. Okay. So that's how we find it. Let's go back and look at part 2. Now let's say we want to estimate lambda squared, which we're going to call gamma. Okay, we're going to call it gamma. So the second part of this was let gamma equal lambda squared. In order to find the minimum variance unbiased estimator, I want to find some function of my sufficient statistic which is unbiased, or which has expectation equal to lambda squared, which is gamma, equal to gamma equals lambda squared. Okay, so we just have to kind of search for it. Let's propose one. What if I take my my MVUE for lambda and I just square it? Let's see what happens. Our intuition tells us it's probably biased, because I know that if I want to estimate a function of a parameter, I usually cannot get away with just taking the same function of my my estimator. But let's see if we can compute this. So this is expected value of basically x bar. Okay, we defined our lambda as just x bar, right? So this was just x bar. Okay, so x bar squared. How in the world do we get the expected value of x bar squared? Well, we should remember that the variance of something is equal to the second moment minus the square of the first moment. So we can rearrange that to get that the second moment is equal to the variance plus the first moment squared. So I'm going to write variance of x bar plus expected value of x bar squared. Okay. The variance of x bar is going to be lambda squared over n, since lambda squared is the variance of the exponential lambda distribution, and I have a sample of size n, so that goes down here. And then expected value of x bar is lambda, and I'm squaring it. Okay, so I get 1 over n plus 1 times lambda squared. Okay, which maybe is nicer. It's nicer to write it as n plus 1 over n lambda squared. So just get a common denominator. So write this second one as n over n. Okay, so actually this estimator is biased for lambda squared. But what I can do is, so remember my gamma is lambda squared, so I'm going to take gamma hat. Let's go ahead and do n over n plus 1 times x bar squared. Okay. If I consider this estimator it has expected value given by n over n plus 1. And then following all of this work I did over here, it's n plus 1 over n times lambda squared, which is lambda squared, which I'm calling that gamma. So this is unbiased. This is unbiased. Moreover, it's a function of the sum of the xi's, okay? Because I can write it as 1 over n sum of the xi's squared, okay? That's like my x bar, okay? So here I've got an unbiased estimator for lambda squared, which is based on a sufficient statistic. So I can write this estimator is the minimum variance unbiased estimator of lambda squared. It means if I'm interested in estimating lambda squared, then among all possible estimators of lambda squared which are unbiased, this one that we just derived has the smallest possible variance. So if I'm going to go with any unbiased estimator, I should definitely go with this one. Let's look at another really familiar situation. We've done this a lot of times, and we've estimated p with p hat, which is just the same as x bar, okay, when we've got an independent random sample from the Bernoulli p distribution. So maybe we should check whether this thing is the minimum variance unbiased estimator for p. But let's pretend we didn't know about this estimator. How would we find from scratch an estimator for p, which is unbiased and has small variance? Well, let's first identify a sufficient statistic. So step 1 is we want to find a sufficient statistic for p. And then step 2 will be find a function of the sufficient statistic which is unbiased for p. Okay, so to find a sufficient statistic, we should turn to the factorization theorem, which requires us to write down the joint probability mass function. Okay, now these are discrete, so let's write p instead of f, because we usually use p for probability mass functions. It's a product, since I've got independent random variables, it's the product of their marginal probability mass functions. So each one is like p raised to the xi, 1 minus p raised to the 1 minus xi. And if we want to include the support, xi has to be either 0 or 1. So xi in the set 0 or 1. Okay, if we simplify, I get like p, so this is going to be like p raised to the x1, 1 minus p raised to the 1 minus x1 times whether x1 is equal to 0 or 1 times all the way out to p raised to the xn, 1 minus p raised to the 1 minus xn times an indicator telling us whether xn is either 0 or 1. And if I take all these p's, I'm going to get p raised to the sum of the xi's. If I take all my 1 minus p's, I'm going to get 1 minus p raised to the n minus the sum of the xi's. okay, because it's like 1 plus 1 plus 1 plus 1 n times, and then I'm subtracting x1 plus x2 all the way out to xn. And then over here I can just write a product of my indicators to pick up these pieces. So by the factorization theorem, I can identify a sufficient statistic for P, which is going to be this sum. Okay, so this is like a function of the sum of the xi's and P, I going from 1 to n. Let me write that more neatly. Xi and P. And here is a function of just the data. And so, so T, x1 through xn, which is the sum of the xi's, is a sufficient statistic for P. Okay, so we finished step 1. We found a sufficient statistic for P, and it's the sum of the xi's. It's not always going to be the sum of the xi's. It is in this case and in the previous example, but we'll find that we get some other answers for different distributions. So now I want to find a function of the sufficient statistic which is unbiased for P. Well, let's think about our P hat. That was like 1 over n times the sum of the xi's. And we know that that was an unbiased estimator of P. So this is unbiased for P, and it's a function of a sufficient statistic. So this is unbiased and a function of a sufficient statistic. Therefore, this P hat n is the minimum variance unbiased estimator for P. Okay, so among all estimators which are unbiased for P, this is the one with the smallest variance. Okay, but you might be asking yourself, what about this estimator we looked at once, which was like y plus 2 over n plus 4, where y was number of successes. Number of successes is just sum of xi's. Okay, so what about this one? Didn't we show that this has lower mean squared error under some values of P? Yes. This estimator, which we get by adding 2 successes and 2 failures to the data, does have a lower mean squared error under some values of P. And I would argue that it's way better. It's a lot of the time way better than P hat. So the minimum variance unbiased estimator is not necessarily always the best estimator. It is the best unbiased estimator. Okay, so this estimator P tilde is not unbiased, remember. By adding 2 successes and 2 failures to the data, we have made the estimator a little bit biased, but we have reduced its variance by a lot. And so sometimes you can introduce some bias to achieve a reduction in variance. Okay. So when we talk about the minimum variance unbiased estimator, we're not really comparing these two estimators because the MVUE has only to do with estimators which are unbiased. Okay, so yeah, this p hat remains the MVUE, but that's not to say that it's absolutely the best estimator you should use. It's only the best unbiased one. Let's do another example. We've got a random sample from a distribution with cumulative distribution function given by this thing. And so here's a parameter floating around. That's the Greek letter eta. And we want to estimate it somehow, so from the data. To give you an idea of why we might be interested in this particular CDF, these CDFs look like this. These are like under different values of eta, under different eta values. The CDF takes these different curves. And this CDF is the CDF of a simplified version of a distribution called the Gompertz distribution. The full Gompertz distribution has an additional parameter, but to simplify the example, I set that parameter equal to 1. Why is that interesting right now? Some people are using the Gompertz function, which is related to the Gompertz distribution, to predict the trajectory of the COVID-19 outbreak. So it is relevant. Okay, so you get these curves. All right, so we're looking at some version with just one parameter, eta, that we want to estimate. And first of all, let's try to find the minimum variance unbiased estimator, which means we need to begin by finding a sufficient statistic for eta. So in part 1, I say, show that this is a sufficient statistic. So you don't even have to find it. We just have to show that this is sufficient. Okay. In order to use the factorization theorem to show that this is a sufficient statistic for eta, we need to write down, we need the joint PDF. So these are continuous random variables because this is a continuous function. We need the joint PDF of x1 through xn, which means I'm going to need to get the PDF which corresponds to this CDF. So first of all, let's just try to get that. Okay. So the PDF corresponding to this CDF we get by just differentiating this guy. Okay, so d by dx 1 minus e to the minus ex minus 1 over eta. It looks like a total mess. It's not so bad. I think we can handle it. We're going to get negative e to the negative e to the x minus 1 over eta. And then by the chain rule, we're going to get minus e to the x over eta. Okay, coming from the top. So let's let me add another page in here. So let's write it out in a nicer way. This minus sign will cancel with this minus sign. So I'm going to have like 1 over eta coming from here. And then e to the x, then e to the minus, e raised to the x minus 1 over eta. And let's remind ourselves about the support, because we see from here that the support is over x greater than or equal to 0. Okay, so that's the PDF. Now, remember, we need to write down the joint PDF of x1 through xn. So the joint PDF of x1 through xn is going to be, since I have independent random variables, which is our random sample, all having the same distribution, their joint PDF can be written as a product of their marginal PDFs. So I'm just going to put xi everywhere I have an x, xi greater than or equal to 0. And what was my task? I want to show that that this sum of e to the xi is a sufficient statistic for eta. So what I want to do is manipulate this until, by the factorization theorem, I can write this as a product of some function of this and eta times a function of just the data. All right, so this product acting on 1 over eta is going to give me just 1 over eta to the power n. Then I'm going to have product of e to the xi. Then I'm going to have product of e to the minus e to the xi minus 1 over eta, and then product of these indicators. Okay, if I look at this thing, this is like e to the x1, e to the x2 times out to e to the xn, which is e raised to the sum of the xi's. Okay, so I'm going to put that over here, e raised to the sum of the xi's. And then I'm going to bring this product of the indicator functions down. Like that. And bring this guy down. This thing is going to be like e raised to the minus ex1 minus 1 over eta times dot 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 e to the minus e to the xn minus 1 over eta. Okay, so these things are all going to get summed. So I can write it as e to the negative sum of e to the xi minus 1 over eta. Okay. And so this part is like a function of only the data values. This part, maybe I need to write this in a slightly different way. Let me distribute the sum to here and to here. So I can write it as this. Okay, because I had sum of e to the xi minus 1. That's like sum of e to the xi minus sum of 1. So e to the xi minus n. Okay, so now I've got a function of the sum of my e to the xi's and of eta times a function which only involves the data. So by the factorization theorem, the statistic, which is the sum of e raised to the xi's, is a sufficient statistic for eta. Okay, so that was step 1. We have shown that this is a sufficient statistic for eta. Now what we want to do is, from there, go on and find an actual estimator for eta. And here is a candidate for the minimum variance unbiased estimator of eta. So eta hat, which is this, we're going to ask, is this the MVUE? Okay. Well, it's already a function of the sum of e to the xi, which is our sufficient statistic. So that was our sufficient statistic. So it's got that going for it. But what we need to show is whether it's unbiased. If so if it is unbiased, then yes, it's the MVUE because it's based on a sufficient statistic. Okay, so what we want to do now is get the expected value of this eta hat. Weird. Okay. We want to get the expected value of this eta hat. So expected value of eta hat is like 1 over n expected value of e to the xi minus 1. All right. If I could figure out this expected value, then I could easily get the expected value of eta hat. So, but I'm going to have to do some work to get this part. So what we're going to do is let's say for x having this density, which was 1 over eta e to the x e to the minus e to the x minus 1 over eta x greater than or equal to 0. Let's consider the function y equals e to the x minus 1. Okay, so let's try to get the expectation of this e to the xi minus 1 by considering a new random variable, which is like e to the x minus 1. And then once we have found the density of this y, then we can find the expected value of y. Okay, as a way of getting this expected value here. So now it just becomes an exercise like one from the beginning of the semester where we're just doing a transformation. So I'm looking at the function y equals e to the x minus 1. That's like my g of x. So the inverse function I can write as log of y plus 1. So if I add 1 to both sides, and then take the log. So this is like my inverse function. And in addition, I've got d by dy of my inverse function is d by dy log of y plus 1, which is 1 over y plus 1. The support, let's think about the support. So x took values beginning at 0 and going up to infinity. So what about y? If I take e to the 0, I get 1 and then subtract 1, so I'm going to get 0. And if I put in larger values of x, this is going to get large. So y has the same support. Okay, so let's write down the PDF of y. I'm going to put down the PDF of x, but wherever I see x, I'm going to put instead log of y plus 1. So I get this. And okay, so then I'm going to do e log y plus 1. Now e. Now up here, this whole ex to the minus 1, I can write as just y. So I have minus y over eta. And now I need to multiply by the absolute value of this, and then indicate the support of my new random variable y. Okay. E and the log cancel each other out, so I'm going to get 1 over eta y plus 1, e to the minus y over eta, like this. And more things cancel. These will cancel. And so I get 1 over eta e to the minus y over eta with support 0 or more. And so we recognize this as the PDF of the exponential distribution with parameter eta. So expected value of y equals eta. That means expected value of e to the xi minus 1 is eta, because up here, that's how I define my y. Okay. So let's go back to our estimator. We had eta hat was 1 over n times the sum of exi minus 1. So the expected value of eta hat is 1 over n sum I equals 1 to n expected value of these guys, which is 1 over n times n eta. Okay, we'll do it in another step. So each of these is just eta, because of the work we did. And so I get 1 over n times n eta, so I get eta. Okay, so expected value of eta hat is eta. So we have an estimator which is unbiased and a function of our sufficient statistic. So it is the minimum variance unbiased estimator, because it's unbiased and it's a function of a sufficient statistic. As a final example, we'll look at a really familiar situation, x1 through xn being a random sample from a normal distribution with mean mu and variance sigma squared. We've been using our whole lives now x bar and Sn squared as estimators for mu and sigma squared. Are these estimators the minimum variance unbiased estimators for their respective parameters? Well, we do know that they are unbiased. We've shown before that this is true. But are they functions of sufficient statistics? Okay, if they're functions of sufficient statistics, then we would say yes, they are the MVUEs. Because remember, to be an MVUE, you have to be unbiased and you have to be a function of a sufficient statistic. That's enough to claim MVUE status. So actually in the previous lecture, we showed that x bar and Sn squared is sufficient for the set of parameters mu and sigma squared. So this pair of statistics is sufficient for this. Okay, so yes, because. So these estimators that we've been using for a long time now are the minimum variance unbiased estimators for mu and sigma. So if we're in this situation of sampling from a normal distribution, if we're wanting to use an unbiased estimator of mu and an unbiased estimator of sigma squared, we can make no better choice than the sample mean and the sample variance.
MVUE, small bias.